Please subscribe to support the channel. At first glance, the sun seems perfectly still, a golden constant in our sky that never changes its position except to rise and set. But this calm appearance is deceptive. In reality, the sun is a vast, churning sphere of plasma that's in constant motion, including spinning on its own axis. Though it looks motionless from Earth, the sun is a dynamic, living star, rotating, boiling, and moving through space with immense energy. Its spin isn't just a trivial fact, it's the driving force behind much of the solar activity we see, from sunspots to solar flares. So yes, the sun spins, and that motion is one of the most powerful and fascinating processes in our entire solar system. While it's easy to imagine the sun as a fixed anchor at the center of the solar system, the reality is far more dynamic. Many people grow up learning that the planets orbit around the stationary sun, but that's an oversimplification, one that hides the fascinating truth of celestial motion. The sun, despite being the gravitational heart of our system, is not motionless. In fact, it moves constantly. Every planet's gravitational pull, especially that of massive giants like Jupiter and Saturn, tugs subtly on the sun, causing it to wobble around a shifting center of mass known as the barycenter. Sometimes this barycenter lies within the sun's body, other times it sits just outside of it. That means the sun itself traces a small, graceful orbit through space, pulled ever so slightly by the collective dance of the planets that circle it. Even beyond this local motion, the entire solar system, sun and all, is orbiting the center of our Milky Way galaxy at roughly 828,000 kilometers per hour, or about 514,000 miles per hour. It takes around 230 million years for us to complete just one galactic circuit. So when we talk about motion in the universe, it's not a simple picture of stillness and orbiting bodies. It's a grand ballet of movement, rotation, and revolution on every scale imaginable. The sun is a moving participant in a much larger cosmic rhythm, constantly shifting its position even as it seems steady to our eyes. Understanding this breaks the illusion of stillness and helps us appreciate that motion, not rest, is the true nature of the universe. As we continue, it becomes important to distinguish the types of motion the sun experiences, because not all motion is the same. This brings us to our next idea, understanding the difference between rotation and revolution, and how the sun does both in ways that shape everything we know about the solar system. To truly grasp the sun's motion, we need to draw a clear line between two often confused concepts: rotation and revolution. These words describe very different kinds of movement, yet together they define the cosmic choreography of our solar system. Rotation is when an object spins on its own axis, just like Earth turning once every 24 hours to create day and night. Revolution, on the other hand, is when an object travels around another body, like Earth, completing one orbit around the sun every 365 days. Now, the sun does both. Yes, it rotates. It spins on its own axis, completing one full turn roughly every 25 days at the equator and 35 days near the poles, a detail we'll explore later. But the sun also revolves, not around another planet or star, but around the center of our Milky Way galaxy. The entire solar system, with all its planets, moons, comets, and asteroids, moves together in this immense galactic orbit. It's as if the sun is both spinning in place and journeying through space at the same time. Imagine for a moment that the sun's rotation is like a spinning top, while its revolution is like that same top rolling across a vast table. The spin and the motion happen simultaneously, each influencing the other. The sun's rotation controls its magnetic fields and solar activity, while its revolution through the galaxy dictates our position in the Milky Way, where we've been and where we're heading across cosmic time. This dual motion underscores a vital truth: nothing in the universe stands still. Every star, every planet, every speck of dust is both rotating and revolving, caught up in an endless cascade of motion. The sun's rotation defines its internal dynamics, while its revolution ties our entire solar system into the greater galactic web. Together, these motions remind us that our cosmic neighborhood is part of something unimaginably vast, a universe in constant, harmonious movement. Now that we understand the kinds of motion the sun experiences, the next step is to explore what the sun actually is. Because to understand how it spins, we first have to know what it's made of. And as we'll soon see, the sun's composition, a fiery ocean of plasma and gas, plays a crucial role in the way it rotates. The sun, our life-giving star, may appear to be a blazing, solid ball of fire when viewed from Earth, but in truth, it's nothing like the rocky world we live on. The sun has no solid surface at all. Instead, it is a vast, seething sphere of plasma, an electrically charged state of matter where atoms are so hot that their electrons are stripped away, leaving behind a soup of nuclei and free electrons. This is not gas in the everyday sense. Plasma behaves differently, interacting intensely with magnetic and electric fields and responding to forces that don't exist in solids or liquids. This difference in composition is key to understanding why the sun's rotation is so unique. On Earth, everything spins together, from the crust beneath your feet to the air above your head, because our planet is a solid, rigid body. When Earth turns on its axis once every 24 hours, every part of it, from the equator to the poles, rotates at the same rate. But the sun doesn't behave that way. Because it's made entirely of plasma and gas, different parts of the sun can move at different speeds, almost as if they're independent of each other. The equator might rotate faster, the poles slower, and the internal layers could move differently still. It's as if the sun's surface, known as the photosphere, is a great ocean of fire, with swirling currents and zones that don't all spin in sync. If we could somehow stand near the sun, which of course we can't, its outer layers reach temperatures of about 5,500 degrees Celsius, and the core burns at around 15 million degrees Celsius, we wouldn't feel solid ground beneath our feet. Instead, we'd be surrounded by luminous gases and plasma streams in perpetual motion. The sun is held together not by a solid structure, but by gravity, which pulls everything inward, balanced against the immense pressure of nuclear fusion pushing outward. That constant tug-of-war keeps the sun stable, even as its outer layers twist, flow, and churn. To understand why the sun behaves this way, imagine it as an enormous dynamo, a cosmic engine powered by its own heat. Deep inside, hydrogen atoms fuse into helium, releasing staggering amounts of energy. That energy then travels outward through the sun's interior, first through the radiative zone, where photons slowly scatter and bounce their way to the surface, and then through the convective zone, where hot plasma rises and cooler plasma sink in great loops of motion. These internal flows are not only responsible for transporting heat, but they also play a major role in the sun's rotation and magnetic activity. Because the sun's matter is fluid, its rotation isn't a single simple spin like a planet's. Instead, think of it as a layered system of motion. The plasma near the equator completes one rotation in about 25 days, while closer to the poles it takes around 35 days. Beneath the surface, in the layers we can't directly see, the rotation patterns are even more complex. The deeper regions, such as the radiative zone, rotate more uniformly, while the outer convective zone is far more turbulent and variable. These differences create shear within the sun, where layers of plasma move at different speeds and directions. That shear is a major source of the sun's powerful magnetic fields and storms. This concept, that the sun's composition affects how it rotates, is one of the most fascinating aspects of astrophysics. On Earth, rotation feels simple and predictable, but on the sun, the laws of motion play out in an environment that's anything but ordinary. Plasma doesn't just move, it flows, swirls, and twists under the influence of magnetic and electric forces. Each region of the sun's surface contributes differently to the overall spin. In essence, the sun's rotation is less like a single solid turn and more like a vast collection of differential motions, each layer and latitude contributing its own tempo to the solar symphony. Another way to picture this is to imagine a gigantic whirlpool made of glowing gas. The center of the whirlpool might spin quickly, while the outer edges move more slowly. The entire structure is in motion, but not uniformly. It's a fluid rotation. The sun's equator spins more swiftly because the centrifugal forces and convective flows there are stronger, while the polar regions, where the flows are more constrained, lag behind. And because there's no solid crust or mantle to tie it all together, there's nothing forcing every region to move at the same rate.
It's also worth noting that this plasma-driven rotation isn't limited to the sun. Many stars exhibit similar behaviors, especially those that are younger and more active. However, the sun's particular structure, with its distinct internal zones and energy flow patterns, makes its rotation especially interesting to scientists. It provides clues not only about how our own star works, but also about stellar dynamics throughout the galaxy. Understanding what the sun is made of and how its fluid nature governs its rotation gives us the foundation to explore one of the most remarkable discoveries in solar science: differential rotation. This phenomenon, which means that the sun doesn't rotate as a single solid body, completely changes how we think about stellar motion, magnetism, and the very structure of stars themselves. As we move forward, we'll dive deeper into this concept of differential rotation, why it happens, how scientists discovered it, and how it shapes nearly every aspect of solar behavior, from sunspots to solar flares, and even the cycles that determine space weather across our solar system. One of the most fascinating and counterintuitive aspects of the sun's motion is something scientists call differential rotation. The idea that the sun doesn't spin as a single rigid body, but instead as a collection of moving layers that rotate at different speeds. This happens because the sun isn't solid like Earth or Mars. It's a vast sphere of plasma. And in a plasma, the forces that govern movement are fluid and dynamic, not rigid or uniform. To understand differential rotation, imagine a giant spinning cloud of glowing gas, so immense that over 1 million Earths could fit inside it. Now picture that every latitude of that cloud, every band from equator to pole, is rotating at its own pace. The equatorial regions complete a full turn in about 25 Earth days, while the mid-latitudes take closer to 30 days, and the polar regions lag behind at around 35 days. This means that if you tracked 2 points, one near the sun's equator and another near the sun's pole, the equatorial point would lap the polar point roughly every 10 days. This uneven motion is what makes the sun's behavior so complex and so mesmerizing. On a solid planet, rotation is straightforward. Everything from pole to pole turns together. But the sun's differential rotation is more like a massive layered storm system, with internal currents and shearing zones that constantly shift and twist. The plasma near the surface doesn't just spin, it's dragged and distorted by magnetic forces, convection, and turbulence. The result is a constant interplay between motion and magnetism, each feeding into the other in an endless loop of energy transfer. The key to understanding why the sun rotates this way lies in its internal structure. Beneath its bright outer layer, or photosphere, the sun is divided into distinct regions that behave differently. Just below the surface lies the convection zone, where hot plasma rises and cooler plasma sinks, creating enormous rolling motions that look like boiling bubbles when viewed close up. These convection flows don't all move in the same direction. Some flow faster, some flow slower. And as they circulate, they tug at the plasma around them, creating local variations in rotational speed. Deeper down, in the radiative zone, where energy is transferred mostly by photons rather than convection, the motion becomes more stable and uniform. This region rotates more like a solid sphere, with less variation from equator to pole. Between these two regions lies a narrow boundary known as the tachocline. And this is an important zone in all of solar physics. The tachocline is where the fast-moving outer plasma meets the slower-moving interior, and this shear layer is believed to be the birthplace of the sun's powerful magnetic field. The twisting and stretching of magnetic field lines here, caused by differential rotation, sets the stage for everything from sunspots to solar flares, and even the cycles that determine space weather across our solar system. If you could somehow see the sun in slow motion, you'd witness an extraordinary sight. Vast currents of plasma flowing across its surface, migrating towards the poles or drifting back towards the equator. These flows change direction over years and decades, altering the sun's magnetic behavior in ways that scientists are still trying to fully understand. The differential rotation doesn't just make the sun spin unevenly, it shapes the star's magnetic personality, driving cycles of calm and chaos that ripple outwards across the entire solar system. Another remarkable feature of this phenomenon is how consistent yet subtly variable it is. The sun has been spinning like this for billions of years, yet its precise rotation rates can fluctuate slightly depending on the solar cycle and the intensity of magnetic activity. During periods of high activity, when the sun produces more sunspots and solar storms, the internal motions can change ever so slightly, altering the flow of plasma and shifting the patterns of rotation. It's as though the sun is breathing, expanding and contracting in rhythm with its own magnetic heartbeat. Scientists often compare the sun's differential rotation to the way Earth's atmosphere behaves. On our planet, the equatorial air moves faster than air near the poles because of the way energy from sunlight is distributed. The sun experiences a similar effect, but on a cosmic scale. Its equatorial regions receive more direct heating and therefore have more vigorous convection, which accelerates their motion. The poles, cooler and less active, move more slowly. The difference is enormous, up to 40% slower rotation at the poles than at the equator, and this difference drives the sun's internal dynamics in spectacular ways. It's worth noting that differential rotation isn't unique to the sun. Many other stars exhibit similar behavior, especially those that are younger and active, but the sun's version of it is particularly well studied because it directly affects us. Every solar flare that erupts, every burst of radiation that sweeps across the solar system, every fluctuation in the space weather that can disrupt satellites or power grids here on Earth, all of it traces back in some way to the sun's uneven spin. When we look at the sun through specialized telescopes, we can sometimes see features on its surface, like sunspots, drift across its face at different speeds depending on where they appear. This is direct, visible evidence of differential rotation in action. Those spots near the equator race ahead, while those near the poles take their time. Over days and weeks, astronomers can actually measure the difference in movement and calculate how fast different regions are spinning. In the simplest terms, differential rotation tells us that the sun is not a rigid machine, but a living system, fluid, responsive, and always changing. It's a reminder that stars are not static lights in the sky, but immense dynamic engines governed by the physics of motion and energy. The sun's differential rotation is the heartbeat of its activity, the driver of its magnetism, and the reason our space environment is as vibrant and sometimes volatile as it is. Now that we've uncovered how the sun spins differently across its surface, it's time to explore this in more detail, starting with how fast it actually spins. In the next segment, we'll focus on the sun's equatorial rotation speed, discovering how astronomers measure it, what it tells us about its internal motion, and why those faster equatorial regions are the starting point for many of the sun's most dramatic magnetic events. When we turn our focus to the sun's equatorial rotation speed, we begin to see just how dynamic and fluid our star is. The equator, the wide middle band of the sun, is the fastest spinning region of its surface. Here, the solar plasma completes one full rotation in approximately 25 Earth days. Compare that to the slower-moving polar regions, where it can take around 30 days for a full rotation, and you immediately understand the sun's extraordinary complexity. This variation in speed, nearly a 40% difference between equator and pole, is one of the defining features of differential rotation, and it plays a vital role in shaping the sun's magnetic and energetic behavior. At the equator, the sun's plasma is constantly in motion, driven by immense convection currents. Hot plasma rises from deeper layers, cools near the surface, and then sinks again in giant loops that can stretch thousands of kilometers across. These swirling motions, combined with the sun's angular momentum, its inherent tendency to keep spinning from its formation, create a region of intense rotational velocity. The equator moves faster because the plasma here isn't held back by the same magnetic and thermal constraints that slow down the higher latitudes. To put this motion into perspective, imagine a spot on the sun's equator, perhaps a dark sunspot, moving across its face.
To complete one rotation, that point travels roughly 2.7 million kilometers per day, which means that in a single second, it covers about 31 kilometers, or roughly 19 miles. That's nearly 3 times faster than a jet airplane. Yet from our view on Earth, the sun seems to hang in the sky, unmoving and tranquil. The reality is that beneath that calm glow lies an enormous sphere spinning with unimaginable energy and momentum. This faster equatorial rotation has enormous implications for how the sun behaves. Because the equator and poles rotate at different speeds, the sun's magnetic field lines, which are rooted in the plasma, get stretched, twisted, and tangled over time. These contortions build up magnetic tension, which can suddenly snap and release in violent eruptions known as solar flares and coronal mass ejections, CNEs. These events blast charged particles into space, sometimes all the way to Earth, where they can disrupt communications, satellites, and even electrical grids. So in a very real sense, the speed at which the sun's equator spins affects not only the sun's magnetic health, but also our own technological world here on Earth. Another fascinating aspect of the sun's equatorial speed is how it reveals the star's internal structure. The sun's surface, or more precisely its photosphere, isn't the only layer in motion. The plasma beneath it, extending thousands of kilometers deep, also spins, and not always at the same rate. Thanks to modern observations from space telescopes and solar probes, scientists have discovered that the radiative zone beneath the sun's convective outer layer rotates more like a solid body, with far less variation between latitudes. It's the outer convective zone, especially near the equator, where the dramatic speed differences appear. This tells us that the sun's energy and motion are not just surface phenomena, they're deeply interconnected processes, woven together from the core to the corona. The faster spin at the equator acts almost like a stirring force, constantly redistributing magnetic and thermal energy across the sun's surface. This motion also drives large-scale flows called meridional currents, where plasma slowly migrates toward the poles and then sinks inward, creating cycles that transport heat and magnetic flux around the entire star. Interestingly, the equatorial spin rate also varies slightly depending on the sun's activity cycle. During periods of high solar activity, when the sun produces more sunspots and solar storms, the differential rotation becomes a bit more pronounced. The equator may spin marginally faster, while the polar regions slow slightly. This subtle change is linked to the shifting patterns of magnetic energy beneath the surface, further proof that the sun's rotation and magnetism are deeply intertwined. You can think of the sun's equator as a kind of cosmic engine, constantly driving the rest of the solar machine. It's where much of the solar dynamo's action begins, where magnetic fields are generated, twisted, and sent spiraling outward. The 25-day rotation period might not sound fast compared to Earth's 24-hour day, but given the sun's sheer size, nearly 1.4 million kilometers across, this rotation rate is astonishing. If the sun were solid, such a spin would tear it apart. But because it's made of plasma, it can move and shift flexibly, maintaining balance through a constant interplay of gravity and pressure. Scientists measure this equatorial rotation using a combination of methods, but one of the most fundamental involves tracking sunspots. When these darker regions appear near the sun's equator, astronomers can follow their motion across the solar disk, timing how long it takes for them to reappear at the same spot after a full rotation. These sunspot observations, first made hundreds of years ago by pioneers like Galileo, provided the earliest clues that the sun was not stationary and not a solid object. Later, with modern tools such as Doppler spectroscopy, scientists can measure the sun's rotation even more precisely by detecting tiny shifts in the wavelengths of light caused by motion toward or away from Earth. The faster motion of the equator compared to the poles may seem like a technical detail, but it's a cornerstone of solar physics. It shapes the structure of the sun's magnetic field, dictates the rhythm of the solar cycle, and even affects the space weather that influences Earth's environment. So in a very real sense, the speed at which the sun's equator spins affects not only the sun's magnetic health, but also our own technological world here on Earth. In short, the sun's equatorial rotation speed is more than just a number.
It's a key to understanding how a star breathes, changes, and evolves. It's the heartbeat of our solar system's central engine, a reminder that beneath its calm glow, the sun is alive with motion and power. As we move forward, we'll turn our gaze from the sun's racing equator to its slower, quieter poles. In the next segment, we'll explore the polar rotation speed, why the poles spin more slowly, and how that difference reveals even deeper truths about the sun's internal dynamics and magnetic mysteries. When we move our attention away from the sun's bustling, fast-spinning equator and look toward its distant poles, we step into a region of striking contrast, a calmer, slower, and more mysterious zone. Unlike the equator, which completes one rotation in about 25 days, the solar poles take roughly 35 days to turn once around their axis. This means the sun's polar regions rotate about 40% slower than the equator, a remarkable difference that tells us one crucial thing. The sun behaves not as a solid body, but as a fluid, dynamic sphere of plasma. This slower polar motion is one of the most compelling pieces of evidence for the sun's differential rotation, the phenomenon we explored earlier. On Earth, a solid planet, every point from pole to equator rotates together. But the sun, being a colossal ball of hot ionized gas, moves in a way that defies that kind of uniformity. Its plasma layers are not locked together, instead they slide, swirl, and flow independently, allowing the equator to race ahead while the poles lag behind. It's a breathtaking reminder that our star is not a fixed machine, but a living, breathing organism of energy and motion. So why do the poles rotate more slowly? The answer lies in the physics of angular momentum and plasma dynamics. At the equator, the sun's rotation carries a greater linear velocity because the circumference there is larger. A point near the equator has much farther to travel in a single rotation. Combine that with the fact that equatorial regions experience more vigorous convective currents, streams of rising and falling plasma that move energy and material, and you get a faster spin at lower latitudes. In contrast, near the poles, the convective motion is weaker, and the plasma behaves more like a slowly circulating eddy than a rushing current. These polar regions are less turbulent, their flows more subdued, resulting in slower rotation speeds. This difference also tells us a great deal about what's happening beneath the surface. The sun's outer layer, known as the convective zone, is where the plasma behaves like a boiling, turbulent fluid, constantly rising, sinking, and sliding across the surface. The deeper radiative zone, lying beneath the convective layer, rotates more uniformly like a solid body. The transition between these zones, the tachocline, is where the sun's internal shear forces are strongest. The slower polar rotation is a natural outcome of how these layers interact. The tachocline, acting almost like a boundary between two rotating systems, transmits the rotational energy unevenly, with the outer plasma layers near the poles being less affected by the rapid movement below. To visualize this, imagine stirring a pot of thick soup. The liquid near the edges moves slower than the liquid near the center, which is directly under your spoon. The sun behaves similarly. The central regions near the equator are constantly being stirred by convective motion and angular momentum transfer, while the polar regions remain calmer, taking longer to complete a turn. But instead of soup, we're dealing with plasma that's thousands of kilometers deep and heated to millions of degrees. The slower polar rotation also has a profound impact on the sun's magnetic field. Because magnetic field lines are frozen into the plasma, they move along with it. Over time, the faster-moving equator drags these lines forward while the slower poles pull them back. This twisting and tangling effect, driven by the differential rotation between equator and poles, is one of the main drivers of the solar dynamo, the process that generates and sustains the sun's magnetic field. It's also the reason why every 11 years, the sun's magnetic poles flip. North becomes south, and south becomes north. In other words, that slow, stately spin at the poles is a crucial part of a much larger story, one that links the sun's rotation directly to its cycles of magnetic activity, solar storms, and even the beautiful auroras that shimmer above Earth's poles.
Without the slower polar motion, the sun's magnetic field wouldn't stretch and twist in the same way, and we might not have the spectacular and sometimes dangerous displays of solar energy that define space weather today. Now, you might be wondering, how do we know all this? After all, the sun's poles are incredibly difficult to observe directly from Earth. From our vantage point in the inner solar system, we always see the sun from roughly the same angle, which means its poles are perpetually tilted away from us. But thanks to decades of scientific innovation, astronomers have found ingenious ways to measure the rotation at these hidden latitudes. The earliest clues came from sunspot tracking. While sunspots rarely appear near the poles, scientists noticed that spots at higher latitudes moved more slowly across the sun's disk than those near the equator, implying slower rotation. Later, with the advent of Doppler imaging, scientists could measure tiny shifts in the light caused by motion. Light moving toward us is slightly blue shifted, and light moving away is slightly red shifted. By analyzing these shifts across the solar surface, researchers could map out the rotation speed at different latitudes, revealing the dramatic slowdown near the poles. More recently, helioseismology, the study of sound waves traveling through the sun, has revolutionized our understanding. By measuring oscillations on the sun's surface caused by internal pressure waves, scientists can infer how the sun's interior is rotating at different depths and latitudes. Through this technique, we've confirmed that the polar regions rotate about 10 days more slowly than the equator, and that this difference extends deep into the sun's outer layers. The slower polar rotation also influences the solar wind, the continuous stream of charged particles flowing outward from the sun into space. The magnetic fields anchored near the poles open outward, allowing solar wind to escape more easily. This flow interacts with the sun's rotation, creating the Parker spiral, a vast swirling pattern of magnetic field lines that fills the heliosphere and envelops all the planets, including Earth. The geometry of this spiral, and therefore the way the solar wind reaches us, depends directly on how fast the sun's poles and equator are spinning relative to one another. It's humbling to realize that the sun's poles, though remote and rarely seen, play such a vital role in shaping the entire solar environment. They are the quiet counterweights to the sun's busy equator, their slower spin helping maintain the balance of the star's magnetic and rotational systems. So when we speak of the sun's polar regions taking about 35 days to complete a rotation, we're not just quoting an astronomical statistic. We're describing one of the most elegant pieces of evidence that our star is alive with motion, fluid, flexible, and governed by the invisible forces of plasma physics. This gentle lag of the poles behind the equator is what keeps the sun's heart beating, what allows it to twist, churn, and send its energy out across the cosmos. And to uncover how we first learned all this, how early astronomers, long before spacecraft and modern sensors, realized that the sun was spinning at all, we must journey back in time. In the next segment, we'll explore how scientists discovered the sun's rotation, beginning with the historic tracking of sunspots across its fiery surface, and how those simple, careful observations changed humanity's understanding of the heavens forever. The discovery that the sun rotates was not made by satellites, Doppler imaging, or advanced spectroscopy. It was made through human eyes, patience, and curiosity. Long before we had the technology to probe the sun's interior, astronomers relied on one of the few visible clues that betrayed the sun's motion: sunspots. These dark, transient blotches on the solar surface became the key to uncovering one of the most profound truths in astronomy: that our star, the very heart of the solar system, is not a still beacon, but a spinning, living sphere. Sunspots are cooler, darker regions on the sun's photosphere, caused by intense magnetic activity that inhibits the upward flow of heat. To the naked eye, they're invisible. You would never see them without a telescope, and it's worth stressing, looking directly at the sun is dangerous without proper protection. But through the early telescopes of the 17th century, astronomers began to notice something astonishing: tiny black dots drifting across the sun's glowing face. The first to record these observations systematically were Galileo Galilei in Italy, Christoph Scheiner in Germany and Thomas Harriot and Johannes Fabricius around 1610 to 1611, only a few years after the invention of the telescope. These early solar observers, using crude lenses compared to today's standards, would project the sun's image onto paper and carefully mark the positions of the spots over time. As days passed, they noticed a consistent pattern. The spots moved steadily from one side of the sun's disk to the other, then disappeared, only to return again after a similar interval. At first, there was fierce debate about what these sunspots actually were. Some astronomers, like Scheiner, believed they were small planets or satellites orbiting close to the sun, crossing in front of it like miniature eclipses. Others, including Galileo, argued that the spots were part of the sun itself, features on or near its surface. The key evidence came from the way the spots changed shape as they traversed the sun's face. They would appear foreshortened near the edges, becoming elongated ellipses as if they were embedded on a spherical surface, just like how continents on Earth appear distorted near the edge of a globe. This was the first convincing clue that the sun wasn't a flat, static disk, but a rotating sphere. By tracking how long it took for a sunspot to travel across the solar disk and reappear on the same side, astronomers estimated that the sun completed one full rotation roughly every 27 days. That value, refined over centuries, corresponds closely to the actual rotation rate of about 25 days at the equator and 35 days near the poles, a remarkable achievement considering the primitive tools of the time. Galileo's drawings of the sun, made in 1612, show the spots shifting positions daily, a clear record of the sun's spin. His meticulous notes transformed sunspots from curiosities into scientific evidence of solar motion. This discovery marked a turning point in human understanding of the cosmos. Until then, the prevailing belief, rooted in centuries of Aristotelian philosophy, was that celestial bodies were perfect, unchanging and motionless, moving only in their grand orbits around Earth or later around the sun. The very idea that the sun could have blemishes, let alone that it could rotate, was revolutionary and even controversial. As observational tools improved, astronomers began to notice even more subtle details. For instance, not all sunspots moved across the sun's surface at the same rate. Spots closer to the equator moved faster, while those at higher latitudes took longer to complete their journey. This variation was the earliest hint of differential rotation centuries before the term existed. Astronomers like Richard Carrington in the 19th century would later formalize these observations, measuring the precise speeds of sunspots at different latitudes and confirming that the sun did not rotate as a rigid sphere. Carrington, who carefully tracked sunspots over decades, discovered not only that the sun rotated faster at its equator, but also that these rotation rates were tied to magnetic activity. He was the first to link a bright solar flare observed in 1859 to a geomagnetic storm on Earth, the infamous Carrington event, which disrupted telegraph systems and caused auroras visible as far south as the Caribbean. His work demonstrated that the sun's spin and its magnetic behavior were deeply connected, a revelation that laid the groundwork for modern solar physics. By the late 19th and early 20th centuries, with the advent of photography, solar observations became more precise. Astronomers could take daily photographs of the sun and measure sunspot motion objectively, free from human drawing errors. These records confirmed what Galileo and others had seen with their own eyes. The sun rotated, and it did so unevenly. Later, spectroscopy allowed scientists to measure the Doppler shifts in light coming from the sun's surface. Light from the side rotating toward Earth was slightly blue-shifted, while light from the opposite side was red-shifted. This provided direct physical proof of rotation, independent of sunspots. What's truly fascinating about this discovery is how it redefined humanity's place in the universe. The realization that even the sun, the source of all life and energy, was not perfect or unchanging, shattered long-held assumptions about the heavens. It reminded us that motion is universal. Everything in the cosmos spins, orbits, and evolves, from the smallest particles to the largest galaxies. The sun's rotation, revealed through the humble tracking of dark patches on its surface, became a symbol of the dynamic, ever-changing nature of the universe itself. Even today, astronomers continue to use sunspots as natural markers to study solar rotation. Modern satellites like NASA's Solar Dynamics Observatory, or SDO, can watch these spots move across the sun's face in incredible detail, producing time-lapse videos that compress days of motion into minutes. It's mesmerizing to watch, dark spots drifting across a roiling, fiery ocean, vanishing at one limb, only to return on the other side. Every one of those motions whispers the same message first heard by Galileo over 400 years ago. The sun spins. The legacy of those early observations is immense. From crude telescopic sketches to sophisticated space-based imaging, the journey of understanding the sun's motion has spanned centuries. And yet, it all began with simple human curiosity and the determination to look a little closer. Now that we've explored how astronomers first uncovered the sun's rotation through the movement of sunspots, it's time to look more closely at the sunspots themselves, what they are, how they form, and why they were and still are such powerful tools for understanding the behavior of our star. Sunspots are among the most striking and mysterious features of our star, dark blemishes that appear, drift, and disappear across the sun's glowing surface like ink stains on a golden ocean. They fascinated astronomers for centuries, not only because of their eerie beauty, but also because they serve as windows into the sun's magnetic heart. These dark patches are not random markings, they're powerful indicators of the sun's internal processes. And they were the very clues that first revealed to humanity that the sun spins. To understand sunspots, we must first understand what makes them appear darker than their surroundings. The sun's surface, or photosphere, burns at an average temperature of about 5,500 degrees Celsius, or 9,932 degrees Fahrenheit. Sunspots, by contrast, are relatively cooler, typically around 3,500 to 4,500 degrees Celsius, or 6,300 to 8,100 degrees Fahrenheit. That's still unimaginably hot by earthly standards, but because they're cooler than the surrounding plasma, they emit less light, making them appear as dark shadows against the sun's blinding brilliance. If you could somehow isolate a sunspot from the rest of the solar disk and view it alone, it would glow fiercely white, brighter than an arc welder and more intense than any flame on Earth. It only appears dark in comparison to the sun's searing background. The cause of these cooler regions is magnetism. Sunspots are areas where the sun's magnetic field lines have become incredibly concentrated, thousands of times stronger than Earth's magnetic field. These magnetic fields erupt from deep within the sun's convection zone and pierce the surface, forming loops that inhibit the normal flow of hot plasma from below. In effect, the magnetic field acts as a lid, blocking convection and reducing the upward transport of energy. With less heat reaching the surface in those regions, the plasma cools slightly, and that cooling in turn creates the dark spot we see. Sunspots don't appear alone. They often come in pairs or groups, connected by enormous magnetic arcs that loop high above the surface. These structures, called solar prominences or magnetic flux tubes, can stretch hundreds of thousands of kilometers into space. From above, the spots mark the points where these magnetic loops enter and exit the sun's surface, like the opposite poles of a magnet. As these fields twist and tangle, they sometimes release vast amounts of energy in the form of solar flares and coronal mass ejections, or CMEs, hurling charged particles across the solar system and influencing everything from satellite electronics to auroras on Earth. What makes sunspots especially important to scientists is that they move, and that motion can be tracked. Since sunspots are embedded in the sun's plasma, they rotate along with it. By measuring how long it takes for a spot to travel across the sun's visible disk and return to the same location, astronomers can calculate the sun's rotation period. When Galileo and other early astronomers tracked these movements in the 1600s, they noticed that spots near the equator completed their transit faster than those near the poles, the first direct evidence that the sun's rotation was not uniform. Over centuries, these observations have allowed scientists to map not just the sun's surface motion, but also its long-term behavior. For example,
By recording the number and position of sunspots over time, astronomers discovered the 11-year solar cycle, a rhythmic pattern in which sunspot activity waxes and wanes. During solar maximum, hundreds of sunspots can pepper the surface, accompanied by intense solar flares and magnetic storms. During solar minimum, the sun can go weeks or even months without a single spot. This cycle is driven by the periodic flipping of the sun's magnetic field, north becoming south and vice versa, a process powered by differential rotation deep within its layers. Each sunspot carries a story about the sun's magnetic field at that moment in time. The direction and strength of its magnetism, the rate at which it drifts across the surface, and even its latitude tell astronomers something about how energy is flowing within the star. Modern space telescopes like NASA's Solar Dynamics Observatory and the Solar and Heliospheric Observatory can observe these spots with incredible precision, capturing minute changes in their motion and magnetic structure. These continuous records allow scientists to model the sun's internal rotation, measure the strength of its magnetic fields, and even predict solar activity that could affect Earth. The story of sunspots is not just about measurement, though. It's about the living rhythm of our star. Each sunspot represents a point of tension in the sun's magnetic web, a visible reminder of the forces that churn beneath the surface. They appear and fade over days, weeks, or months, sometimes merging or breaking apart as magnetic fields shift. Their birth and decay are directly tied to the sun's internal engine, the same processes that drive the light and heat that sustain life on Earth. Sunspots also connect us across centuries of discovery. From Galileo's hand-drawn sketches to high-resolution imagery from orbiting satellites, humanity has been watching these dark specks for over 400 years, building an unbroken record of the sun's changing face. This record, known as the sunspot number, has become one of the most valuable data sets in all of astronomy. It shows how solar activity has varied across centuries, including quiet periods like the Maunder minimum in the 17th century, when almost no sunspots were seen for decades, coinciding with a time of cooler climate on Earth known as the Little Ice Age. In a way, sunspots are the sun's pulse. Their appearance and disappearance tell us when the star's magnetic field is calm or chaotic, when it's about to burst with energy or settle into slumber. They are the fingerprints of solar motion and magnetism, revealing that the sun is far from a static object. It is alive, with patterns, cycles, and storms that ripple across space.
And beyond their scientific value, there's something deeply poetic about them. To think that a few dark specks on the surface of a distant star could lead to the discovery of its spin, its magnetism, and its cycles, that through those marks we've come to understand not only how the sun moves, but how it breathes, is a powerful reminder of how observation connects us to the universe. Now that we understand what sunspots are and how they help us track the sun's rotation, we can turn our gaze back to history. The next step in this cosmic journey is to look at the early astronomers, Galileo, Scheiner, Carrington, and others, who used sunspots to unravel the mysteries of the sun's motion and magnetism, forever changing how humanity saw its place in the cosmos. The story of how humanity discovered the sun's rotation is one of the most profound turning points in the history of science. A moment when human curiosity, armed with new tools of observation, revealed that even the most majestic and seemingly divine body in the heavens was not perfect, still, or unchanging. It was a revelation that shook the foundation of philosophy and our understanding of the universe itself. And it all began with the simple act of watching, patiently, day after day, as dark spots drifted across the brilliant face of the sun. It's the early 1600s, a time when the telescope has just entered the world of science. The device, barely a decade old, is being used by pioneering astronomers to explore a universe no one had truly seen before. Among them was Galileo Galilei, a name that would come to symbolize the clash between observation and old belief. With a crude telescope made of glass lenses and a wooden tube, Galileo turned his instrument toward the heavens and saw a cosmos far different from the perfect, eternal realm described by Aristotle. He saw mountains and craters on the moon, moons orbiting Jupiter, and, most controversially, blemishes on the very face of the sun itself. These blemishes, sunspots, were not unique to Galileo's eyes. Around the same time, several other astronomers across Europe were making similar observations. Thomas Harriot in England, Johannes Fabricius in the Netherlands, and Christoph Scheiner in Germany all reported dark spots crossing the sun's surface. Yet their interpretations differed.
Many, including Shiner at first, believed that these spots were tiny planets or clouds orbiting close to the sun, like Mercury, but smaller and invisible except when silhouetted against the solar disk. The reasoning was simple. The sun, as a source of divine light, must be perfect and untarnished. The idea that it could have flaws seemed impossible, even blasphemous. But Galileo challenged that assumption head-on. By projecting the sun's image onto a sheet of paper and sketching the spots each day, he realized that the same features reappeared and moved across the solar face in a consistent pattern. He noticed that they started near one limb of the sun, drifted steadily across its disk, and disappeared at the opposite edge. After about 2 weeks, they would reappear on the starting site again. This, Galileo concluded, could only mean one thing: the sun itself was rotating. In his letters and drawings, Galileo recorded these patterns meticulously. He noted that the spots changed shape as they approached the sun's edges, appearing elongated near the limbs and more circular when near the center. This observation was critical. It suggested that the spots were not separate bodies passing in front of the sun, but rather features on a spherical surface. The foreshortening effect, similar to how continents appear distorted on a globe viewed at an angle, proved that the sun was a rotating sphere. Galileo estimated that the sun completed one full rotation in about 27 days, remarkably close to modern measurements. He had, through simple observation, uncovered a fundamental property of our star that would take centuries to fully understand. His discovery was revolutionary, not just for astronomy, but for the worldview of his time. Because Galileo's findings directly contradicted centuries of Aristotelian philosophy, which taught that celestial bodies were perfect, immutable, and distinct from the corruptible Earth, they stirred immense controversy. The idea of a spotted sun implied that the heavens were dynamic and imperfect. To many scholars, this was an unsettling notion. Galileo, already under suspicion for his support of the heliocentric model, that the planets orbit the sun, not Earth, now seemed to be undermining the very notion of divine perfection in the heavens. Despite the controversy, Galileo's work sparked a wave of scientific excitement. His correspondence with Shiner, though at times contentious, helped refine methods for observing and measuring solar phenomena. Both men continued to study the sun, each convinced of their interpretations, but history would favor Galileo's conclusion that the spots were features on the sun's surface. In the decades and centuries that followed, other astronomers built on Galileo's foundation. Christoph Shiner, using improved telescopes, made detailed drawings of sunspots and their paths, confirming the sun's rotation and even noting the inclination of its axis relative to the ecliptic plane. His monumental work, Rosa Ursina, published in 1630, became a cornerstone of early solar physics. Later, astronomers like Jean-Dominique Cassini and Giovanni Domenico Maraldi in the 17th century continued observing sunspots, refining the sun's rotation ray and noting the variation in movement at different latitudes, the first hint of differential rotation. By the 18th and 19th centuries, the telescope had become an essential scientific instrument, and solar observation was more precise than ever. Astronomers like Heinrich Schwabe spent decades tracking sunspot numbers, eventually discovering the 11-year solar cycle, the periodic rise and fall of solar activity. This finding, published in 1843, connected the sun's visible surface features to its internal magnetic processes and opened the door to understanding the sun not as a static source of light, but as a dynamic, evolving star. Then came Richard Carrington in the mid-1800s, whose name remains immortal in solar history. Carrington not only mapped sunspot movements to confirm differential rotation, that the equator rotates faster than the poles, but also made the first direct connection between solar activity and terrestrial effects. In 1859, while observing a large sunspot group, Carrington witnessed a sudden flash of intense light, a solar flare, that reached Earth hours later, causing a massive geomagnetic storm that disrupted telegraph systems worldwide and produced auroras as far south as the Caribbean. This Carrington event was humanity's first realization that solar activity could directly impact our planet.
From Galileo's humble sketches to Carrington's detailed maps, these discoveries transformed our understanding of the sun. What began as simple drawings of dark spots evolved into a scientific revolution, linking the sun's motion, magnetism, and energy to the very fabric of the solar system. Each observer, Galileo with his quill and parchment, Shiner with his meticulous diagrams, Schwabe with his decades of patience, and Carrington with his precise timing, contributed to a grand narrative that revealed the sun as an active, rotating, magnetic star. Today, when solar observatories and spacecraft monitor the sun with instruments capable of capturing every pulse of its activity, they are continuing the work that began in those early telescopic observations. Every modern image of the sun's surface, every measurement of its rotation and magnetic fields, stands on the shoulders of those first astronomers who dared to suggest that the sun was not perfect, that it turned, changed, and lived. The discovery that the sun rotates was more than just a scientific milestone. It was a philosophical awakening. It shattered the illusion of celestial perfection and showed that the same laws of motion that govern Earth also govern the heavens. The sun's rotation became a bridge between humanity and the cosmos, linking our small spinning world to the vast spinning machinery of the universe itself. Now that we've seen how Galileo and his successors unveiled the sun's rotation through centuries of observation, our next step is to explore another crucial aspect of solar motion: the tilt of the sun's rotational axis. This small but significant inclination affects how we see the sun from Earth and plays a subtle yet important role in our understanding of its behavior. The sun's axis tilt is one of those subtle details that might seem minor at first glance, yet it has profound implications for how we observe and understand our star's motion. Unlike Earth, which is tilted at about 23.5 degrees, giving us our familiar seasons, the sun's rotation axis is tilted by a smaller but significant 7.25 degrees relative to the plane of Earth's orbit, a plane known as the ecliptic. This slight inclination might seem trivial compared to the grand scale of the sun itself, but from our vantage point on Earth, it changes how we see the sun's face throughout the year and influences how we measure and interpret its rotation. To visualize this, imagine the sun as a spinning sphere whose poles don't align perfectly with the plane of Earth's orbit. Instead, it's tipped just enough that as Earth moves around it, our line of sight shifts slightly above and below the sun's equator. Over the course of a year, this tilt means that sometimes we're looking a bit down toward the sun's north pole, and 6 months later, we're looking slightly up toward its south pole. It's like watching a spinning globe from a slightly changing angle. The top tilts toward you part of the time and away from you at others. This 7.25-degree tilt has a few important effects on solar observation. The first is the apparent path of sunspots. Because the sun's equator is not perfectly aligned with the ecliptic, sunspots don't seem to move in a perfectly straight line across the sun's disk. Instead, their motion appears slightly curved, shifting subtly north or south depending on the time of year. When the sun's north pole is tilted toward Earth, around early September, we can see a bit more of the northern hemisphere. By early March, the south pole tilts toward us, giving us a clearer view of the southern hemisphere. These periodic shifts are subtle but measurable, and they're critical for solar astronomers who track the movement of sunspots to determine rotation rates and magnetic activity. If the sun weren't tilted, the apparent motion of these spots across the disk would be simpler, a straight left-to-right movement from our perspective. But because of the tilt, their paths curve slightly, and the angles of their motion change throughout the year. Scientists account for this by using something called the heliographic coordinate system, which maps sunspot positions on the sun's surface just as latitude and longitude do on Earth. Without adjusting for the sun's tilt, we wouldn't be able to accurately determine where on the solar surface a sunspot truly lies. The tilt also gives rise to an observable phenomenon called the B0 angle, which describes how much of the sun's north or south pole is tilted toward Earth at any given time. When B0 is positive, we're looking more toward the north pole. When B0 is negative, we're peering more toward the south pole. The maximum value of this angle, about plus 7.25 degrees or minus 7.25 degrees, occurs twice a year, corresponding to those times when the sun's rotational axis points most toward or away from us. These subtle changes affect not just sunspot tracking, but also the way we see large-scale solar features like coronal holes and prominences, which can appear and disappear depending on the viewing angle. The tilt of the sun even affects how scientists interpret data from solar missions. Spacecraft like SOHO, SDO, and the Parker Solar Probe continuously monitor the sun, but their positions relative to Earth and the sun's axis must be precisely accounted for. Even a small misalignment can lead to errors in calculating the sun's rotation speeds or magnetic field distributions. That's why scientists use the tilt angle to correct their observations, ensuring that when they say a sunspot is at, say, 10 degrees north latitude, it truly corresponds to that position on the solar surface, not just a projection from our skewed viewpoint.
Interestingly, the sun's tilt doesn't just affect what we see. It also hints at the history of our solar system. The fact that the sun's rotational axis is not perfectly aligned with the ecliptic plane raises intriguing questions about how the solar system formed. The planets orbit roughly within the same flat plane, the remnant of the original disk of gas and dust that collapsed to form the sun and its family of worlds. So why is the sun's axis slightly tilted relative to that plane? One possible explanation is that gravitational interactions over billions of years, particularly with the gas giants Jupiter and Saturn, have slowly altered the sun's orientation. Another hypothesis suggests that early asymmetries in the protoplanetary disk, or even the impact of massive magnetic forces during the sun's formation, could have caused the slight tilt. Whatever the cause, that 7.25-degree difference reminds us that even our solar system, so orderly and balanced, bears traces of its turbulent birth. For observers on Earth, this tilt gives the sun a gentle nod throughout the year, a subtle celestial rhythm that goes largely unnoticed by casual stargazers but is vital to astronomers. It adds a quiet complexity to the way we perceive our star, a slow cosmic wobble that reveals how dynamic and alive the sun really is. Beyond observation, the sun's tilt also plays a role in shaping the solar magnetic cycle. Because the magnetic field lines emerge and migrate differently at various latitudes, the way we see those movements from Earth depends on the sun's orientation. During periods of high solar activity, when sunspots and magnetic regions cluster around dead latitudes, the tilt affects how we perceive their drift toward the equator during the cycle's progression. Without accounting for this geometry, our measurements of magnetic field reversals and polar dynamics would be incomplete. In essence, the sun's axis tilt is a small but crucial detail that connects observation, geometry, and cosmic history. It's one of those features that doesn't shout its importance, but quietly influences everything we know about the sun's rotation and magnetism. It's also a reminder that perspective matters. The way we see the universe, even something as familiar as our own star, depends on where we stand and how we're oriented. So the next time you watch a time-lapse of sunspots drifting across the sun's glowing surface, remember that the graceful curves they trace aren't random. They're shaped by a 7.25-degree tilt that subtly shifts our view of a spinning star, a tilt that connects our perspective here on Earth to the slow, majestic dance of the sun in space. Now that we understand how the sun's tilt affects our perception of its rotation, it's time to explore why the sun spins at all. In the next segment, we'll dive into the cause of the sun's rotation, tracing it back billions of years to the very moment our solar system was born, when a swirling cloud of gas and dust collapsed to form the shining star we know today. To understand why the sun spins, we need to journey back more than 4.6 billion years to a time before the sun, the planets, or even the concept of a solar system existed. In that distant era, our region of space was nothing more than a vast, cold cloud of gas and dust, stretching light years across. It was a silent sea of hydrogen, helium, and tiny grains of heavier elements forged in earlier generations of stars. Yet even in this apparent stillness, there was motion, subtle, delicate, and ancient. That motion, known as angular momentum, would become the reason why the sun and everything that orbits it spins to this day. Every star, every planet, and every moon carries with it a kind of cosmic fingerprint, its spin. This rotation is not something that appeared by accident or random chance. It is the natural consequence of one of the universe's most fundamental laws, the conservation of angular momentum. This law states that when a rotating system contracts, when it shrinks in size, it spins faster, just as a figure skater pulls in their arms to spin more rapidly. The sun's rotation is a direct product of this process, a legacy inherited from the ancient swirling cloud that gave it birth. Let's imagine that primordial solar nebula, the cloud of gas and dust that eventually collapsed to form our solar system. For reasons that might have included the shock wave from a nearby supernova or gravitational instabilities within the Milky Way, this enormous cloud began to collapse under its own gravity. As it contracted, it didn't fall straight inward like a rock dropping to the ground. Instead, because the cloud already had even a minuscule amount of spin, that rotation became more pronounced as it shrank. This happens because of angular momentum conservation. As the radius of a rotating object decreases, its speed of rotation must increase to conserve the total angular momentum. It's the same principle that causes a spinning ice skater to twirl faster when pulling their arms close to their body. The collapsing gas cloud flattened into a disk, spinning faster as it condensed. In the center of that disk, matter began to accumulate, densifying, heating, and eventually igniting nuclear fusion to form the sun. Thus, the sun's spin was inherited from the rotation of the solar nebula itself. Every particle that fell into the newborn sun contributed its share of angular momentum, adding to the star's spin. Meanwhile, the remaining material in the disk coalesced into planets, moons, asteroids, and comets, all orbiting in roughly the same plane and direction as the sun's rotation. That's why, to this day, nearly all the planets in our solar system orbit the sun in the same direction that it spins, a cosmic echo of that original swirling motion. But the story doesn't end with simple inheritance. Once the sun began to form and ignite, complex magnetic interactions started to shape and regulate its rotation. As the sun's magnetic field coupled with the surrounding disk of gas, it exerted a braking force, slowing the sun's spin slightly as it transferred angular momentum outward into the disk. This magnetic braking helped prevent the sun from spinning too fast, because if it had rotated much more rapidly, centrifugal forces could have disrupted the young star's formation. In other words, the sun's magnetic field acted like a cosmic governor, keeping its spin stable enough for the star to form properly, and for the planets to coalesce safely within the protoplanetary disk.
Even after the sun reached maturity, this interplay between magnetism and motion continued. Over billions of years, the sun's rotation has gradually slowed due to a process known as magnetic braking, or stellar wind drag. The sun constantly emits a flow of charged particles, the solar wind, which carries away a small but steady amount of angular momentum. This process acts like a continuous, gentle brake on the sun's spin. In its youth, the sun likely rotated much faster, perhaps once every few days. But as it aged, this solar wind has gradually robbed it of rotational energy, slowing it to its current rate of roughly once every 25 days at the equator. This slowing process isn't unique to the sun. It's a universal feature of star evolution. Young stars, still surrounded by their disks, spin rapidly and glow with intense magnetic activity. Over time, their magnetic fields interact with their stellar winds, gradually transferring angular momentum away from the star. As a result, older stars rotate more slowly and exhibit less magnetic turbulence. This relationship between a star's age and its rotation speed is so reliable that astronomers use it to estimate stellar ages, a method known as gyrochronology. So, when we observe the sun spinning today, we are witnessing a cosmic relic of motion, a spin that began before the sun existed, inherited from the galaxy's primordial dynamics, and slowly refined by billions of years of physics. That motion connects our star to the universe's earliest processes, stretching back to the chaotic birth of stars themselves. It's worth noting how elegantly this story ties everything together. The same principle of angular momentum that makes a child's spinning top wobble or an ice skater twirl faster also governs the dance of galaxies, the spin of planets, and the motion of the sun.
It's one of those rare cases in science where a simple rule applies seamlessly from the smallest scales to the largest. The conservation of angular momentum is one of the universe's quiet but unyielding laws. It ensures that motion is never lost, only transformed. Interestingly, some astronomers have wondered whether the sun's relatively slow rotation today might hint at its early interactions with the forming planets, especially Jupiter, the solar system's giant. The gravitational interplay between the sun and the surrounding protoplanetary disk could have redistributed angular momentum, possibly helping to shape the orbital structure of the planets. In this sense, the sun's rotation rate may not only be a record of its own formation, but also a clue to how the entire solar system came into being. If we could have observed the sun in its infancy, we would have seen a young, blazing sphere spinning much faster, its surface alive with violent storms, magnetic eruptions, and an intense stellar wind. Over billions of years, as its energy stabilized and its magnetic field matured, that spin gradually calmed. The sun we see today is the product of that long evolution, still spinning, still carrying the momentum of its birth, but tempered by time and the subtle forces of magnetism. In short, the sun spins because the universe is never still. Motion is the default state of nature, and angular momentum is the language of that motion. From the first collapse of the nebula to the steady glow we see now, the sun's rotation is a story written in the mathematics of movement, a story that connects our star to the very fabric of cosmic creation. And the effects of that rotation are far from trivial. In fact, the sun's spin plays a vital role in shaping its behavior and activity, influencing everything from its magnetic field to the dramatic phenomena we see on its surface. In the next segment, we'll explore exactly that, how the sun's rotation affects its activity, including its magnetic fields, its solar storms, and the cycles of energy that ripple through the solar system like a cosmic heartbeat. The sun's rotation is far more than just a graceful spin in space. It's the beating heart that drives nearly every dynamic process on and within our star. It fuels its magnetic fields, shapes its surface activity, and powers the rhythmic rise and fall of the 11-year solar cycle, a repeating pattern of calm and chaos that influences everything from sunspots and solar flares to the flow of radiation through the entire solar system. The sun's rotation is not just motion, it's energy in motion, transforming the sun from a passive source of light into a living, breathing engine of cosmic weather. To appreciate how rotation affects the sun's behavior, we first have to understand that the sun's magnetic field is not static or simple. Unlike Earth's relatively stable magnetic field, which is generated by the motion of molten metal in its core, the sun's field is created by the movement of electrically charged plasma deep within it. This magnetic field is immense and complex, constantly twisting, stretching, and tangling under the influence of the sun's rotation. Because the sun does not spin as a solid body, its equator rotates faster than its poles, the magnetic field lines embedded in the plasma become distorted over time. Imagine painting a straight line around a balloon and then twisting the balloon unevenly from the top and bottom. That line would begin to warp and coil, exactly what happens to the sun's magnetic field lines as they're dragged along by differential rotation. Over the course of months and years, these lines wrap around the sun, forming intricate loops and knots that store enormous amounts of energy. Eventually, these tangled fields become so twisted that they burst through the sun's surface, forming sunspots, dark regions where intense magnetic fields inhibit the upward flow of heat. These magnetic knots can also snap, reconnect, and release their pent-up energy in violent explosions known as solar flares or coronal mass ejections. Such eruptions hurled vast quantities of charged particles and radiation into space, sometimes directly towards Earth. When these solar storms reach our planet, they can trigger spectacular auroras at the poles and, in extreme cases, disrupt satellites, power grids, and communication systems.
All of this, every flare, every sunspot, every magnetic loop that arches over the sun's surface, is fundamentally driven by rotation. Without the sun's spin, its plasma wouldn't shear and flow in the way needed to generate such a dynamic magnetic field. The rotation acts as the engine of a process scientists call the solar dynamo, the self-sustaining mechanism that continually regenerates the sun's magnetic field. This solar dynamo operates deep within the sun, especially in a region known as the tachocline, which lies between the uniformly rotating radiative zone and the turbulent convective zone. Here, the faster-moving outer layers rub against the slower-moving inner ones, creating immense shear forces. These forces stretch and twist magnetic field lines, converting kinetic energy, from rotation, into magnetic energy. The interplay between the sun's internal motion and its magnetic field produces a constantly shifting magnetic landscape, and the result is the solar cycle. The solar cycle is one of the most remarkable natural rhythms in our corner of the universe. It spans roughly 11 years, during which the sun's magnetic field completely reverses polarity. The north magnetic pole becomes the south, and vice versa. At the beginning of a cycle, the sun is relatively calm, with few sunspots and little magnetic disturbance. This is called solar minimum. As the cycle progresses, differential rotation winds the magnetic field tighter and tighter, leading to more sunspots, more flares, and more coronal mass ejections. The sun enters a period of heightened activity known as solar maximum. During solar maximum, the sun's face can be covered with dozens or even hundreds of sunspots, some larger than Earth itself. Solar flares can erupt daily, and the corona, the outermost layer of the sun's atmosphere, becomes bright and active, filled with magnetic loops and high-energy plasma. Eventually, the tangled magnetic field becomes so stressed that it reorganizes itself, snapping into a new configuration and flipping its polarity. This marks the peak of the cycle. Afterward, the magnetic field begins to unwind. Activity gradually declines, and the sun returns to solar minimum, ready to begin the cycle anew. This cycle has been observed for centuries through the careful counting of sunspots. It was first identified in the 1840s by Heinrich Schwab, a German amateur astronomer who spent 17 years sketching the sun every clear day, noting how the number of sunspots rose and fell in a repeating pattern. Later, astronomers like Edward Maunder and George Hale connected these patterns to changes in solar magnetism. Hale, in the early 20th century, discovered that sunspot pairs have opposite magnetic polarity, and that this polarity reverses with each new 11-year cycle, meaning the sun's full magnetic cycle actually spans about 22 years. The rotation-driven solar cycle doesn't just affect the sun itself. It influences the entire heliosphere, the vast bubble of charged particles that extends far beyond Pluto. When the sun is active, the heliosphere expands and strengthens, shielding the solar system from cosmic rays. When the sun is quiet, this protective shield weakens, allowing more cosmic radiation to reach the inner planets, including Earth. This changing solar environment impacts everything from satellite electronics to astronaut safety, and even, to a certain degree, Earth's upper atmosphere and climate. Another fascinating consequence of the sun's rotation is how it shapes the structure of the solar wind. The constant flow of charged particles emanating from the sun doesn't stream straight outward. Instead, it's influenced by the sun's spin, forming a massive spiral pattern known as the Parker spiral. This spiral fills the solar system, and its geometry means that solar storms and magnetic fields from the sun can sweep across the orbits of planets in complex, wave-like patterns. In essence, the sun's rotation is what transforms it from a simple sphere of glowing gas into a magnetically alive star. It's what gives rise to the phenomena that define solar weather, what sustains the cycles that shape the space environment, and what connects the sun's internal motion to its farthest reaches of influence. Without rotation, the sun would still shine, but it would be a much quieter, simpler star, lacking the pulsating rhythms of activity that make it so dynamic and fascinating. Rotation, therefore, is not just a mechanical property of the sun. It's the heartbeat of its energy system. It drives the magnetic dynamo, modulates the solar cycle, and breathes variability into the star's otherwise constant light. Every flare, every sunspot, every ripple in the solar wind, all of them trace their origins back to that simple fact: the sun spins. And what ties all of this together, what truly makes the sun's behavior so extraordinary, is the deep connection between its rotation and its magnetic field. The twisting and coiling of those invisible magnetic lines, all born from the sun's uneven spin, are the ultimate architects of solar activity. In our next segment, we'll explore that connection in detail, uncovering how the sun's rotation and differential motion generate, twist, and sometimes violently release the magnetic forces that shape the very heartbeat of our solar system. The sun's magnetic field is one of the most powerful and dynamic forces in our solar system, a vast, invisible web of energy that stretches from the solar interior out past the orbit of Pluto. It is the true architect behind most of the sun's fascinating and sometimes violent behaviors. From sunspots to solar flares to coronal mass ejections, or CMEs, nearly every solar phenomenon that stirs the space environment begins with the twisting, tangling, and breaking of magnetic field lines deep within and above the sun's surface. And what drives this endless magnetic drama? The answer lies in the sun's differential rotation, the uneven spinning of its plasma across different latitudes and layers.
To understand this connection, we first have to remember that the sun is made of plasma, not solid matter. Plasma is a state of matter in which electrons are stripped from atoms, creating a sea of charged particles that can conduct electricity. Because plasma is electrically conductive, it interacts strongly with magnetic fields. In fact, the magnetic field lines in the sun are effectively frozen into the plasma. Wherever the plasma moves, the magnetic field lines move with it. Now, imagine this immense sphere of plasma rotating. Not evenly, but at varying speeds. The equator spins once every 25 days, while the poles take about 35 days. Over time, this differential rotation causes the magnetic field lines, which were once relatively simple and aligned with the sun's poles, to become stretched and twisted. It's as if the sun is constantly winding its own magnetic threads, turning them into tightly coiled springs of energy. This twisting effect is especially intense in the tachocline, the thin boundary layer between the sun's inner radiative zone and its outer convective zone. Here, the smooth, uniform rotation of the inner regions meets the turbulent, fast-moving plasma of the outer layers. The resulting shear forces generate complex magnetic motions, the essence of the solar dynamo. This dynamo converts kinetic energy from rotation and convection into magnetic energy, continuously regenerating the sun's magnetic field and feeding its dynamic activity. As the sun's magnetic field becomes more tangled, parts of it begin to emerge through the surface. These emerging loops of magnetism appear as sunspots where they pierce the photosphere, the visible layer of the sun. Each sunspot marks 1 foot of a magnetic loop, one end where the field exits the surface and another where it re-enters. Between these sunspot pairs, immense arcs of magnetism rise high into the sun's atmosphere, creating structures called prominences and coronal loops. But the sun's surface and atmosphere are constantly shifting, driven by convection, the boiling motion of plasma that transports heat outward. As these flows move the magnetic field lines around, they stretch and twist them even further. Eventually, the tension becomes too great, and the magnetic fields snap and reconnect in a process known as magnetic reconnection. When that happens, energy that has been stored for days or weeks is released in just seconds or minutes, producing massive bursts of radiation and charged particles. These events are what we observe as solar flares, sudden brilliant flashes of light and X-rays that can outshine the rest of the sun for a brief moment. In even more extreme cases, the reconnection process hurls billions of tons of plasma into space in a coronal mass ejection, or CME. These CMEs are among the most powerful explosions in the solar system, capable of sending charged particles hurtling through space at speeds of up to 3,000 kilometers per second. When directed toward Earth, they can compress our planet's magnetic field, cause geomagnetic storms, and produce vivid auroras in the sky.
It's astonishing to realize that all of this, these breathtaking eruptions, these storms that ripple across millions of kilometers, begins with the sun's rotation. The faster equator, the slower poles, and the turning convective flows beneath the surface all work together to twist magnetic field lines like taut rubber bands. Without differential rotation, the sun's magnetic field would remain relatively simple, and the sun itself would be far quieter. Instead, this uneven motion turns the sun into a cosmic dynamo, a generator of magnetic storms that shape the very conditions of space around us. As the magnetic field lines are wound tighter and tighter, the sun's magnetic polarity eventually begins to reverse. The north magnetic pole becomes the south, and vice versa. This reversal happens approximately every 11 years, defining the solar cycle that governs the rise and fall of solar activity. During solar maximum, when the field is at its most tangled and complex, the sun is a boiling cauldron of magnetic storms, its surface alive with sunspots, flares, and CMEs. Then, as the field reconfigures and untangles, the sun moves into solar minimum, a calmer period when activity drops and the magnetic field lines return to a simpler, more dipole-like configuration. This constant magnetic evolution creates the solar corona's intricate structure, the outermost layer of the sun's atmosphere, visible during a total solar eclipse. The bright streamers, loops, and plumes seen extending outward from the sun are shaped entirely by magnetic fields sculpted by differential rotation. Even the solar wind, the continuous flow of charged particles streaming away from the sun, follows these magnetic patterns. Where magnetic fields are open, particles escape freely into space. Where they're closed, they loop back, trapping plasma and creating the glowing arcs seen in ultraviolet images. In a very real sense, the sun's magnetic field is the link between its internal motion and its external influence. The differential rotation deep within the sun doesn't just affect what happens on the surface, it sends ripples of energy outward across the entire solar system. The Earth's magnetic field, the behavior of satellites, even the radiation environment on Mars and the edge of interstellar space, all are touched by the invisible hand of the sun's rotation-driven magnetism. What's even more remarkable is that this process is universal. Other stars show similar magnetic cycles and eruptions, though they vary in intensity and period. Younger, faster-spinning stars have more powerful magnetic fields and more frequent flares, while older stars, like the sun, gradually slow down and mellow with age. Our sun, now halfway through its life, is in a relatively moderate phase, active enough to shape space weather, but stable enough to sustain life on Earth. So when we see those awe-inspiring images of solar flares leaping from the sun's surface, or when auroras light up the night sky after a geomagnetic storm, we're witnessing the visible signature of an invisible dance, the twisting of magnetic fields by a rotating fluid star. The sun's spin and its magnetism are inseparable, partners in an eternal choreography that has been unfolding for billions of years and will continue for billions more. And that raises an intriguing question. What if this dance were to stop? What if the sun didn't spin at all? What would happen to its magnetism, its flares, and the balance of the solar system itself? In the next segment, we'll explore this fascinating hypothetical, how the absence of rotation would transform the sun from a dynamic, living star into something far quieter and far less capable of sustaining the world we know.
Let's imagine, for a moment, a universe in which the sun does not spin. A universe where our bright, burning star simply hangs in the void, stationary, unmoving, perfectly still. It continues to shine, of course, powered by the nuclear furnace deep within its core, but it no longer rotates on its axis. At first glance, that might sound like a small change. After all, the sun's spin doesn't seem to affect its brightness or warmth from our perspective on Earth. But in truth, such a still sun would be an entirely different kind of star. Its physics, its magnetism, its behavior, and even the conditions throughout the solar system would be profoundly altered. Rotation is not a trivial feature of stars. It is one of their defining properties. The sun's spin isn't just a graceful motion, it's a vital source of energy transformation, responsible for driving convection, magnetism, and activity in the solar atmosphere. Without rotation, the sun would lose the very mechanisms that give it character and life. The calm, stable light we depend on would remain, but the vibrant, ever-changing face of the sun, the sunspots, solar flares, magnetic fields, and dynamic corona, would vanish. The sun would become an almost unrecognizable object, a quiet, static, magnetically dead sphere of glowing plasma. The first and most dramatic change would occur in the sun's magnetic field. Today, the sun's magnetic activity is powered by the solar dynamo, a self-sustaining process that arises from the interaction of differential rotation and convective motion. In essence, the sun's rotation converts kinetic energy, movement, into magnetic energy, creating the powerful magnetic fields that thread through its plasma. If the sun stopped spinning, that dynamo would shut down. Without the shearing forces that twist and stretch magnetic field lines, there would be no way to regenerate the magnetic field once it decayed. Over time, perhaps in a few thousand or million years, the sun's magnetic field would simply fade away. The surface would no longer produce sunspots, since those are regions where magnetic field lines burst through the photosphere. Solar flares and coronal mass ejections, which depend on the snapping and reconnection of those magnetic fields, would cease entirely. The sun's corona, the glowing outer layer that extends millions of kilometers into space, would lose much of its structure and energy. The spectacular loops and streamers seen during solar eclipses would fade into a faint, uniform halo. The solar wind, the continuous stream of charged particles emitted by the sun, would weaken drastically, as it is largely guided and accelerated by magnetic fields. The disappearance of the solar wind might sound like a blessing for Earth. Fewer geomagnetic storms, fewer disruptions to satellites and power grids, but it would come with consequences. The solar wind carves out a protective bubble around the solar system called the heliosphere, which shields us from high-energy cosmic rays originating beyond our galaxy. Without a strong solar wind, the heliosphere would collapse inward, exposing Earth and the other planets to a much greater flux of cosmic radiation. Over long timescales, this could have subtle but real effects on planetary atmospheres, including our own. The absence of rotation would also change the sun's internal dynamics. Currently, the sun's equatorial regions rotate faster than its poles, creating immense shear in the boundary layer known as the tachocline. This shearing motion is critical to the dynamo process, but it also affects convection, the up and down flow of plasma that transports heat from the interior to the surface. Without rotation, convection would likely become more symmetrical and less chaotic. The sun's outer layers might become more uniform with fewer large-scale flows or currents. This could slightly alter the way heat is distributed across the surface, potentially leading to a more even and consistent emission of light. From a visual standpoint, the sun's surface would appear far less interesting. Today, we see a constantly changing landscape of sunspots, bright flares, and turbulent granules, the visible signs of magnetic and convective activity. A non-rotating sun would lack most of these features. It would still shine just as brightly, the energy from nuclear fusion in its core would continue unaffected, but its appearance would be smooth, almost featureless, like a perfect glowing orb. The sun's variability, which influences the solar cycle and modulates the amount of energy reaching the upper atmosphere, would be gone. The solar cycle itself, the rhythmic 11-year pattern of activity and calm, would cease to exist. Ironically, this would make the sun more stable, but also less protective. Without magnetic storms and solar flares, the space environment around Earth would become calmer in some ways. Fewer disruptions to radio communications, no geomagnetic storms. Yet, at the same time, the sun's lost magnetism would allow more cosmic radiation to penetrate the inner solar system. The balance between solar and galactic forces that define our cosmic neighborhood would tilt in favor of the latter. There's another subtle effect to consider: the impact on the planets themselves. The sun's rotation doesn't just affect its magnetic field, but it also contributes in a small way to the gravitational balance of the solar system. A spinning sun bulges slightly at its equator due to centrifugal forces. This equatorial bulge exerts a minor but measurable influence on the orbits of the planets, especially Mercury. If the sun stopped spinning, that bulge would disappear, altering the gravitational field just enough to slightly shift planetary orbits over long timescales. While not catastrophic, it would be yet another reminder that motion, even rotational motion, shapes the architecture of our cosmic home.
Moreover, a non-rotating sun would change the very nature of its identity as a star. Stellar rotation plays a crucial role in a star's evolution, influencing everything from how it distributes elements in its interior to how it loses mass over time. Without spin, the sun's internal mixing would slow, affecting the way hydrogen and helium are cycled within its layers. Over billions of years, that could slightly alter the sun's life expectancy and the way it transitions into a red giant at the end of its life. But perhaps the most profound consequence of a motionless sun would be symbolic. The sun's spin is a thread that connects it to every other object in the cosmos. From the smallest asteroid to the largest galaxy, everything in the universe rotates. Rotation is one of the most fundamental properties of matter, a natural outcome of how things form and move in a gravitationally bound universe. A non-rotating sun would be an anomaly, a break in the cosmic rhythm. Its stillness would stand as an unnatural silence in a universe defined by motion. So, if the sun did not spin, we would still have light and warmth, but the sun's soul, its dynamic magnetism, its living pulse of activity would be gone. It would no longer be the restless creative star that shapes space weather and drives the cycles of energy that ripple through the solar system. Instead, it would be a static lamp in the sky, eternal and unchanging, and, in a sense, lifeless. Thankfully, that's not the universe we inhabit. Our sun spins, slowly and unevenly, yes, but beautifully so, and that spin gives rise to everything that makes it vibrant. The same rotation that turns 1 billion tons of plasma every second also fuels the auroras that dance in our skies and protects us from the harsh cosmic rays beyond our solar system. The sun's spin is not just a motion, it's a heartbeat, one that pulses through every aspect of solar and planetary life. Now that we've explored what would happen if the sun didn't rotate, let's return to reality and to the tools that allow us to measure its motion today. In the next segment, we'll look at how modern scientists track and map the sun's rotation with extraordinary precision, using Doppler measurements, space telescopes, and helioseismology to see the sun's spin in action, not just on its surface, but deep within its hidden interior. In the modern era of astrophysics, our understanding of the sun's rotation has evolved far beyond what Galileo and his contemporaries could ever have imagined. What once required months of careful sketching through early telescopes can now be measured in real time, with precision so fine that scientists can detect variations in the sun's rotation down to just a few meters per second. We no longer rely on only watching sunspots drift across the surface. Today, we can see the sun's interior spin, map the movement of its plasma layers, and even listen to the sound waves reverberating inside it. The story of how we measure the sun's rotation today is one of technology, innovation, and persistence, an unbroken chain from the earliest telescopic drawings to the cutting-edge observatories orbiting our star right now. At the heart of this modern revolution are a few key techniques: Doppler spectroscopy, helioseismology, and space-based solar imaging. Together, these methods have transformed the sun from a distant glowing disk into a dynamic, measurable system whose every motion we can now observe in stunning detail. Let's begin with one of the most fundamental tools, the Doppler effect. This principle, familiar with the way an ambulance siren changes pitch as it passes by, applies equally to light. When an object moves towards us, the wavelength of its light are slightly compressed, blue shifted. When it moves away, the wavelengths are stretched, red shifted. By measuring these tiny shifts in the light emitted from the sun's surface, astronomers can determine how fast various parts of the sun are moving relative to Earth. Using Doppler spectroscopy, scientists observe one side of the sun's disk moving slightly toward us, blue shifted, and the opposite side moving away, red shifted, as it spins. This provides a direct and precise measurement of the sun's rotation speed. With this technique, we've confirmed that the sun's equatorial regions rotate once about every 25 days and its polar regions about every 35 days. But Doppler measurements do more than just tell us how fast the surface spins. They also reveal subtle flows within the solar atmosphere, such as meridional currents that carry plasma from the equator towards the poles and back again. However, the sun's most profound mysteries lie beneath its surface, hidden from view by layers of glowing plasma. To probe those depths, scientists use an extraordinary technique called helioseismology, the study of sound waves that travel through the sun. The sun, in a sense, rings like a bell. Its turbulent convection zone constantly generates waves that ripple through the solar interior, causing the surface to oscillate, rising and falling by just a few kilometers. By studying these oscillations, scientists can infer the sun's internal structure and rotation, much like seismologists on Earth study earthquakes to learn about our planet's interior.
When sound waves move through the sun, they're affected by the density, temperature, and motion of the material they pass through. If a part of the sun is rotating faster, the waves traveling in that direction move differently than those traveling in the opposite direction. By measuring these differences using Doppler imaging and precise timing, scientists can create a three-dimensional map of how the sun rotates at various depths. This is how we discovered that the sun's radiative zone, its inner region where energy travels mainly by radiation, rotates almost uniformly, while the convective zone above it exhibits differential rotation, faster at the equator, slower at the poles. Between these layers lies the tachocline, where the rotation changes abruptly and where the sun's magnetic dynamo is believed to operate. Without helioseismology, we might never have known this internal structure existed. It's like hearing the sun's heartbeat and realizing that beneath its calm exterior lies a world of complex motion. The data that make this possible come from a fleet of dedicated solar observatories, both ground-based and in space. One of the most important is NASA's Solar and Heliospheric Observatory, SOHO, launched in 1995. SOHO carries an instrument called the Michelson Doppler Imager, MDI, which has been crucial in mapping solar oscillations and rotation patterns. The MDI produced some of the first detailed 3D models of the sun's internal dynamics, confirming theories about how the differential rotation extends deep beneath the surface. Following SOHO, NASA's Solar Dynamics Observatory, SDO, launched in 2010, took solar observation to an entirely new level. Its helioseismic and magnetic imager, HMI, captures ultra-high-resolution images of the sun every few seconds, providing a continuous real-time record of its motion and magnetic field. HMI doesn't just show sunspots. It tracks the subtle Doppler shifts across the entire solar disk, allowing scientists to measure the sun's rotation with astonishing accuracy. Every twist and swirl on the sun's surface is recorded, analyzed, and modeled to reveal the ever-changing patterns of flow beneath. In addition to these, the Global Oscillation Network Group, GONG, a system of 6 ground-based observatories located around the world, provides 24-hour coverage of the sun's vibrations. GONG's continuous monitoring allows researchers to detect long-term variations in rotation and magnetic activity, complementing data from space-based missions. Together, they create a seamless picture of the sun's dynamics, one that spans from its visible surface down to the hidden layers below. In recent years, even more ambitious missions have joined the effort. The Parker Solar Probe, launched by NASA in 2018, is traveling closer to the sun than any spacecraft in history, diving through the sun's outer atmosphere to study how rotation, magnetism, and the solar wind interact. Meanwhile, the European Space Agency's Solar Orbiter, launched in 2020, is providing unprecedented views of the sun's polar regions, helping to refine our understanding of how the poles contribute to the global rotation and magnetic cycles. What's truly remarkable about these modern techniques is their precision. Scientists can now detect minute variations in the sun's rotation rate over time. For instance, slight speeding up or slowing down linked to changes in solar activity.
They can also study how rotation varies with depth, revealing that the outer layers of the convective zone rotate differently from the deeper layers, and that even the core might have its own unique spin rate. These findings are crucial not just for solar physics, but for our understanding of how stars evolve, since rotation plays a central role in stellar life cycles. In essence, our sun has become one of the best measured objects in the universe. From its surface movements to its hidden interior, every twist and oscillation is cataloged and analyzed, helping scientists piece together the complex mechanics of a rotating star. What began as Galileo sketches of sunspots drifting across the solar face has evolved into a global, high-tech symphony of instruments listening to and watching the sun as it turns, a triumph of human curiosity and ingenuity. And yet, for all that we've learned, the sun still holds secrets. Beneath its radiant layers, deep within its core, lie mysteries that even our most advanced tools can only hint at. Our next step in this journey takes us inside, to explore the sun's internal rotation, the hidden motion that flows through its layers like cosmic currents and powers its magnetic and thermal life from within. Deep beneath the sun's blinding surface, beyond the shimmering currents and sunspot-studded layers we can observe directly, lies a world of invisible motion, an internal system of rotation so intricate and layered that even after decades of study, scientists are still unraveling its mysteries. The sun's spin isn't confined to the surface we see. It permeates every layer, from the fiery core where nuclear fusion takes place to the turbulent convective zone that bubbles and churns just below the visible photosphere. But here's the astonishing truth. These layers don't all rotate together. Each moves to its own rhythm at its own pace, shaped by physics as ancient as the universe itself. When scientists talk about the sun's internal rotation, they're referring to the way different zones within the sun's structure spin and how those motions interact to create the magnetic and thermal behavior we observe. Thanks to decades of research, particularly through helioseismology, we now know that the sun is not a simple uniform rotator. Instead, it is divided into three main regions that each exhibit distinct rotational characteristics: the core, the radiative zone, and the convective zone. Let's begin at the very heart, the core. This is the sun's engine room, the site where hydrogen atoms fuse into helium under immense pressure and temperature, releasing the energy that powers all sunlight. The core extends from the sun's center out to about 25% of its radius, and while we cannot observe it directly, helioseismic data gives us tantalizing clues about its motion. For many years, astronomers assumed that the core rotated at roughly the same rate as the rest of the sun. However, more recent measurements suggest something remarkable. The core may rotate faster than the outer layers, perhaps even up to 4 times faster than the surface. This differential behavior in the core is still a topic of active research, but it likely stems from the sun's formation. During its birth from a collapsing cloud of gas and dust, angular momentum, the property that governs spin, was distributed unevenly as the sun contracted. The dense core may have retained more of this original spin, while the outer layers slowed down over billions of years due to magnetic braking and the solar wind. If the core truly rotates faster, it could serve as a reservoir of angular momentum that slowly transfers energy outward, influencing the sun's long-term magnetic evolution. Surrounding the core is the radiative zone, a vast region extending from about 25% to 70% of the sun's radius. Here, energy generated in the core travels outward primarily in the form of radiation, photons bouncing from one particle to another in a long, slow, random walk that can take thousands or even millions of years to reach the surface. Unlike the chaotic churning in the outer layers, the radiative zone is remarkably stable. Helioseismic studies show that this region rotates almost uniformly,
behaving much more like a solid body. The stability of the radiative zone is crucial to the sun's overall balance. The pressure and density are so immense that turbulence is largely suppressed, allowing the plasma to move cohesively. This uniform spin contrasts sharply with the outer layers above it, where convection dominates and motion becomes much more complex. The radiative zone's steady spin also serves as a kind of internal anchor for the sun's rotation, providing a foundation against which the faster variable motion of the outer layers exerts constant tension. And then we come to the convective zone, the sun's outermost layer, which makes up roughly the last 30% of its radius. Here, energy transfer changes character completely. Instead of radiation, convection takes over. Hot plasma rises from the bottom of the zone, cools as it nears the surface, and sinks back down, creating vast, roiling cells of motion known as granules and supergranules. These convective flows are visible on the sun's surface as a pattern of bright and dark modeling, each granule about the size of Texas. It's within this convective zone that the sun's famous differential rotation emerges most vividly. At the equator, plasma completes one full turn in about 25 days, while near the poles, the rotation stretches out to 35 days. This difference in speed sets up shear forces, layers of plasma sliding past each other. And it's this shearing motion that plays a key role in generating the sun's magnetic field through the solar dynamo. Between the radiative zone and the convective zone lies one of the most fascinating and mysterious layers in all of solar physics, the tachocline. This is a narrow transition region, only a few percent of the sun's radius thick, where the uniform rotation of the radiative zone meets the chaotic differential rotation of the convective zone. The tachocline is thought to be the cradle of the sun's magnetism. Here, the twisting and stretching of magnetic field lines reach their most extreme, amplifying weak field into the powerful, large-scale magnetic structures that dominate solar activity. Without the tachocline and the contrasting motions of the sun's internal layers, the solar dynamo might not exist at all. The difference in rotation rates between the stable radiative zone and the turbulent convective zone provides the raw energy needed to sustain the sun's magnetic cycles. The tachocline acts like a gear, converting the steady spin of the interior into the swirling magnetic complexity that manifests on the surface. What's truly remarkable is that these internal rotations are not static. They evolve subtly over time, influenced by changes in magnetic activity and the sun's age. For example, during periods of intense solar activity, the peaks of the 11-year solar cycle, small but measurable changes occur in the sun's internal rotation rates, particularly near the tachocline. These fluctuations may play a role in the timing and strength of solar cycles, linking the deep interior to the visible surface in a delicate and dynamic feedback loop.
Our understanding of these hidden motions comes primarily from helioseismology, the science of studying oscillations within the sun. Using data from instruments like SOHO's Michelson Doppler Imager, MDI, and the Helioseismic and Magnetic Imager, HMI, aboard NASA's Solar Dynamics Observatory, scientists can measure thousands of distinct oscillation modes across the sun's surface. Each mode penetrates to different depths, revealing the rotation rate and density of the material it passes through. Together, these measurements paint a three-dimensional map of how the sun's interior spins, a stunning achievement of modern astrophysics. This picture reveals that the sun's motion is far more complex than a simple rotation. It's a layered symphony of movement, a slow-turning core, a steady radiative body, and a chaotic convective ocean, all interacting through invisible magnetic threads. Each layer influences the others, balancing forces of gravity, pressure, and motion to maintain the sun's stability. In a way, the sun's internal rotation mirrors the intricate rhythms of the cosmos itself. It's a reminder that beneath the apparent calm of nature lie deep interconnected processes, a balance of energies and motions that sustain the universe's beauty and complexity. And just as the sun's internal spin shapes its magnetic and thermal life, so too does it connect to the wider family of stars. In our next segment, we'll step beyond the sun to compare its rotation with that of other stars, discovering how a star's age, size, and mass affect how fast it spins,
and how that spin in turn reveals a story of its life in the cosmos. When we look beyond our sun to the countless stars scattered across the Milky Way, we find that rotation, that graceful cosmic spin, is not unique to our star. In fact, it's a universal trait among stars, a fundamental result of how they form and evolve. Yet while every star spins, not all spin alike. A star's rotation rate tells a story about its age, its mass, its magnetic field, and even its past. By comparing the sun's measured spin to that of other stars, astronomers can place our star within a grand continuum of stellar evolution, revealing how rotation changes as stars age and how this subtle motion shapes their lives in the cosmos. The sun, with its leisurely rotation, about 25 days at the equator and 35 days at the poles, is a middle-aged star in terms of both age and spin. It's roughly 4.6 billion years old, about halfway through its main sequence lifetime. Its rotation rate has slowed considerably since its youth, when it likely completed a rotation in just a few days. This deceleration is a natural part of stellar evolution, and it happens to nearly every star in the universe. Younger stars, particularly those just a few 100 million years old, spin much faster than the sun. Some rotate once every day or two, whipping around with speeds that can reach tens or even hundreds of kilometers per second at their equators. Their rapid rotation fuels extraordinarily strong magnetic fields and intense stellar activity. These young stars often exhibit frequent massive flares, powerful coronal mass ejections, and wildly variable brightness as magnetic storms erupt across their surfaces. In many ways, these stars resemble what our sun must have looked like in its infancy, a volatile, energetic object surrounded by the remnants of its protoplanetary disk, spinning fast and throwing off radiation in bursts. But as stars age, their rotation begins to slow, a process primarily driven by magnetic braking. This mechanism is remarkably elegant. As a star rotates, it generates a magnetic field that extends into space and couples with the stellar wind, the constant stream of charged particles flowing outward. These particles carry away not just mass, but also angular momentum, the physical property that governs rotational speed. Over billions of years, this slow leakage of angular momentum causes a star's rotation to decelerate. The stronger the star's magnetic field and stellar wind, the faster it loses angular momentum and the faster its spin slows. The sun, therefore, sits at a kind of cosmic middle ground, neither as frenzied as a young star nor as lethargic as an ancient one. Its rotation is balanced, its activity relatively moderate. It still produces flares, sunspots, and solar storms, but they occur in a predictable rhythm, the 11-year solar cycle, rather than the chaotic outbursts of youth. This stable, mature phase has likely persisted for billions of years and will continue for billions more, creating the steady conditions that have allowed life on Earth to thrive. When astronomers observe other stars similar to the sun, called G-type main sequence stars, they can trace a clear relationship between rotation rate and age. Younger G-type stars spin rapidly, older ones slow down. This relationship is so consistent that scientists use it to estimate a star's age based on its rotation, a method known as gyrochronology, from gyro meaning rotation and chronos meaning time. By measuring how quickly a star spins, astronomers can determine its approximate age even when other dating methods are uncertain.
Interestingly, a star's mass also plays a significant role in how it spins. More massive stars, such as A-type or B-type stars, which are larger, hotter, and more luminous than the sun, rotate much faster. Some complete a rotation in just a few hours. Their surfaces can move at speeds of hundreds of kilometers per second, so fast that the stars become oblate, bulging noticeably at the equator due to centrifugal forces. These rapid rotators often have weaker magnetic fields and thinner outer convection zones, meaning they don't experience magnetic braking as effectively as the sun. As a result, they maintain their high rotation speeds for much of their lifetimes. In contrast, smaller, cooler stars, such as K-type and M-type red dwarf stars, tend to spin more slowly, especially as they age. These stars have deep convection zones and powerful magnetic fields. which cause them to lose angular momentum efficiently. Early in their lives, they may rotate rapidly, but over time, they slow dramatically, becoming magnetically quiet. However, because red dwarfs can live for trillions of years, many we observe today are still in relatively active, fast-spinning stages compared to their main sequence lifespans. The relationship between rotation and magnetism also helps explain why the sun's activity level is moderate compared to younger or older stars. Fast rotation amplifies magnetic fields, which in turn increases flare activity and stellar winds. As stars slow down, their dynamos weaken, their magnetic fields decay, and their activity levels decline. This means that stars, like living organisms, experience a kind of magnetic aging. Young stars are loud and energetic, their magnetism flaring like tempests. Middle-aged stars like the Sun are calmer, but still active. Old stars grow quiet, their once turbulent fields fading into tranquility. The study of stellar rotation has been revolutionized by missions like Kepler and TESS, which have provided high-precision light curves of thousands of stars. By observing the periodic dimming and brightening caused by star spots rotating in and out of view, much like sunspots on our sun, astronomers can measure the rotation periods of stars across a wide range of ages and masses. This vast dataset has confirmed that the sun's current rotation fits perfectly within the expected curve for a star of its age, mass, and activity level. One fascinating outcome of these comparisons is the realization that our sun is unusually stable. Many sun-like stars of similar age still show higher magnetic activity or irregular cycles. The sun's consistent rhythm, its steady, predictable magnetic reversals and moderate flares, may be relatively rare. This stability could be one reason why life on Earth has had the time and calm environment to evolve uninterrupted for billions of years. In the broader stellar context, the sun isn't special because it spins. Every star spins. But it is special because of how it spins. Slowly enough to be stable, fast enough to remain magnetically alive, and precisely balanced between youth and old age. Its rotation tells us that it's a star in its prime, mature and harmonious, quietly sustaining the cosmic conditions that define our solar system. And this spin doesn't just define the sun itself, it influences everything around it. The sun's rotation shapes the heliosphere, the magnetic bubble that shields our solar system, and affects the motion of charged particles, solar winds, and cosmic rays throughout the interplanetary medium. In our next segment, we'll explore exactly that, how the sun's rotation connects and governs the larger structure of the solar system, influencing not only its magnetic boundaries, but the very space weather that reaches Earth and beyond. The sun's spin does not end at its surface. Its influence stretches far beyond, threading through the entire solar system in invisible streams of magnetic energy and charged particles. Every rotation of the sun sets in motion a vast spiraling pattern of plasma and magnetism that envelops all 8 planets, every moon, comet, and grain of interplanetary dust. This immense rotating magnetic bubble, known as the heliosphere, is one of the most extraordinary and far-reaching consequences of the sun's rotation. The heliosphere can be thought of as the sun's magnetic atmosphere, inflated by the solar wind, a continuous flow of charged particles, mainly electrons and protons, that stream outward from the sun in all directions. These particles are born in the sun's outer layers, where magnetic activity and heat propel them into space at speeds of hundreds of kilometers per second. But because the sun is rotating, this outflow doesn't simply shoot straight outward like light rays. Instead, it twists into a vast spiral pattern known as the Parker spiral, named after the solar physicist Eugene Parker, who first described it in 1958. Imagine holding a garden hose and letting water spray from the nozzle. If you spin in a circle while keeping the water flowing, the stream will curve into spirals rather than moving in straight lines. The same thing happens on a cosmic scale. As the sun spins once every 25 to 35 days, it drags its magnetic field lines and the solar wind into enormous spiraling structures that extend far beyond Pluto, more than 120 astronomical units from the sun, or roughly 18 billion kilometers. This entire region, shaped by the sun's rotation and magnetism, defines the bubble of space dominated by the sun's influence. Inside the heliosphere, the sun's magnetic field is not just an abstract force. It is a living, twisting structure that constantly interacts with the solar wind. As the sun rotates, its magnetic field lines wrap around themselves, creating regions of compression and rarefaction that travel outward through the solar wind like ripples. These ripples form what scientists call the heliospheric current sheet, a massive, undulating sheet of electric current that extends through the entire solar system. The heliospheric current sheet is sometimes described as the largest structure in the solar system. It's shaped like a wavy ballerina skirt, a delicate but powerful pattern that oscillates as the sun's magnetic field changes during its 11-year cycle. Every time the sun's magnetic field flips polarity, with north and south reversing, the current sheet warps and reshapes, sending waves of magnetic change coursing through interplanetary space. These waves can take days, weeks, or even months to reach the outer planets, subtly influencing the local space environment as they pass.
The charged particles carried by the solar wind and the magnetic fields they drag along create a dynamic, rotating system that protects our entire solar neighborhood. The heliosphere acts as a shield against cosmic rays, deflecting many of the high-energy particles that originate from outside the solar system. Without this magnetic cocoon, Earth and the other planets would be bombarded by much higher levels of radiation, which could have profound effects on atmospheres, climate, and even biological evolution. The sun's rotation, by driving the magnetic processes that sustain the heliosphere, is therefore directly responsible for one of the key forms of protection that make life on Earth possible. But the sun's spin doesn't just shape the large-scale structure of the heliosphere, it also drives space weather, the constantly changing flow of energy and particles that travel through the solar system. As the sun rotates, regions of intense magnetic activity, sunspots, flares, and coronal holes, come into and out of view, periodically releasing bursts of plasma and radiation. These emissions propagate through the solar wind, sometimes catching up with slower-moving streams, creating shock waves that ripple across the heliosphere. When these waves reach Earth, they can interact with our magnetic field, triggering geomagnetic storms and auroras. Space weather, in essence, is the solar system's response to the sun's rotating magnetic personality. Because the sun's magnetic field is twisted and carried outward by its rotation, it forms sectors of alternating polarity in the solar wind, regions where the magnetic field points either toward or away from the sun. As Earth orbits through these sectors, it experiences variations in solar wind pressure and direction, which can modulate cosmic ray intensity, alter radio propagation, and even subtly affect climate systems. The rotation of the sun also influences the solar wind structure and speed. Fast solar wind streams originating from coronal holes near the sun's poles can rotate into alignment with slower streams from equatorial regions. When these differing flows collide, they form co-rotating interaction regions, or CIRs, massive rotating fronts of compressed plasma and magnetic field. These CIRs are carried outward by the solar wind, sweeping through the solar system like rotating weather fronts, and can cause minor geomagnetic storms when they encounter planets. Over time, the constant interplay of these rotating flows gives the solar wind a texture and variability that's directly tied to the sun's spin. Beyond the outer planets, the effects of the sun's rotation continue to dominate. Even at the heliopause, the boundary where the solar wind's pressure is finally balanced by the interstellar medium, the imprint of the sun's rotation can still be detected in the shape and direction of magnetic fields. Data from NASA's Voyager 1 and Voyager 2 spacecraft, which have now traveled beyond the heliosphere, show that the solar magnetic field still influences the environment billions of kilometers from home.
The sun's slow spin, its 25-day rhythm, echoes faintly even at the edge of interstellar space. The sun's rotational influence on the solar system is not merely a physical effect, it's a unifying force. Everything within the heliosphere, every planet, comet, and particle of dust moves within this grand magnetic bubble, connected by the same rotating field. The sun's rotation, therefore, isn't confined to the star itself, it defines the magnetic architecture of the entire solar system. If the sun didn't spin, there would be no Parker spiral, no heliospheric current sheet, and no structured solar wind. The magnetic field would still exist, but would extend outward in straight static lines, offering far less protection and variability. The solar system would be a quieter but far more vulnerable place, exposed to the full fury of the interstellar medium. Instead, because our sun rotates, the space between planets is alive. The sun's spin gives shape to space weather, sculpts magnetic landscapes billions of kilometers wide, and connects Earth's auroras to magnetic storms on the far side of the sun. Its motion binds the planets together in a single dynamic system, a vast magnetic ocean whose tides are driven by the slow, steady turning of our star. And that brings us full circle to the final realization of this cosmic story. The sun does indeed spin, and its spin is the source of the motion, magnetism, and vitality that permeate our entire solar system. In our concluding segment, we'll bring together everything we've learned from the sun's differential rotation to its magnetic heartbeat to answer the question that began our journey once and for all. Yes, the sun spins, and its spin is the heartbeat of our solar system. After this long and fascinating journey through the heart of our star, through its glowing surface and deep interior, through its magnetism, motion, and influence across billions of kilometers, we can finally return to the simple question that started it all. Does the sun spin? And the answer, clear, elegant, and profound, is yes. The sun absolutely spins. It may not appear to from our distant vantage point here on Earth, but the sun is a dynamic, rotating sphere at plasma, a star alive with motion, constantly turning, shifting, and breathing energy into every corner of the solar system. What we once mistook for stillness is in fact a grand celestial dance, a rotation that defines the sun's very nature and shapes everything it touches.
The sun's spin is not a slow, meaningless drift. It is the driving force behind nearly all of its visible and invisible behaviors. Its rotation winds magnetic fields like cosmic threads, powering the storms and flares that ripple across its surface. It generates the solar dynamo, the heart of its magnetic engine, which flips the sun's polarity every 11 years in an endless cycle of renewal. It propels the solar wind that fills interplanetary space, carves out the vast heliosphere that shields our solar system, and creates the glowing auroras that shimmer in Earth's polar skies. The sun's rotation is, quite literally, the heartbeat of our solar environment. Every sunspot that drifts across the sun's face, every flare that erupts from its corona, every wave of charged particles that sweeps through the solar system, all of it stems from that simple cosmic motion. The sun spinning on its axis. The sun turns, and by turning, it breathes life into the space around it. Its spin fuels the patterns of magnetism and light that reach every planet, shaping climates, protecting worlds, and governing the rhythm of cosmic weather that surrounds us. And it's not alone in this. Every star in the universe, from the smallest red dwarf to the largest blue giant, carries the same fundamental motion. Rotation is a universal language of the cosmos, a remnant of the spin of the ancient clouds of gas and dust that gave birth to stars, planets, and galaxies alike. The sun's rotation connects it to that grand cosmic lineage. It reminds us that motion is woven into the fabric of creation itself. When you stand under the daylight sky and feel the warmth of the sun on your skin, you're not just feeling the light of a star, you're feeling the energy of motion. The photons that began their journey in the sun's core are released from a star that has been spinning for 4.6 billion years, turning with the rhythm of its birth cloud, carrying the angular momentum of the universe forward in time. And though the sun's rotation has slowed since its fiery youth,
It will continue to spin for billions of years to come, even as it ages and transforms into a red giant in the far future. That spin, the same motion that keeps its plasma flowing and its magnetism live, will persist until the end of its stellar life, a silent echo of the forces that shape the cosmos.
So when we ask, does the sun spin? We're really asking something deeper. Is the sun alive with motion? Is it connected to the same forces that shape galaxies, planets, and the dance of the universe itself? The answer to all of these questions is yes. The sun's spin is not just a fact of astronomy, it's a reminder of the beauty and unity of the cosmos, a universe where everything moves, turns, and evolves in harmony. Our sun is not a motionless lamp in the sky. It is a rotating, dynamic star, a cosmic engine of energy and magnetism. Its steady spin sustains the magnetic storms that color our skies, drives the solar wind that defines the boundaries of our world, and keeps the heartbeat of our solar system in motion. So the next time you look up at that blinding golden disk, remember, the sun is turning, slowly, silently, endlessly. And with every rotation, it continues to weave the invisible web of light and motion that binds together the entire solar system, including us. The sun spins, and because it spins, our world shines. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.